think that's 29. I will be away. I'd rather be here. Okay, number 17. Here they give us the function x over x plus 1. Sorry, that's x plus 2. Let me remind you, if you want the derivative of a quotient, so p is some function of x, q is some function of x, here's what you do. There's no other way other than just memorizing this. Denominator times the derivative of the numerator minus numerator times the derivative of the denominator over the denominator squared. Yeah, this numerator, it looks like a mixed product, but it's negative. So it's important which comes first. Subtraction's not commutative. It's denominator times derivative of numerator minus numerator times derivative of denominator over the denominator squared. And let me warn you, it's not so much on the first midterm as it is on the second midterm. I'm not sure why. It is not the case that the derivative of a quotient is the quotient of the derivatives. That's not the quotient rule. You do that on the second midterm, and I don't need to read any further. You're wrong. Also, this is not as fatal, but you're still wrong. People get the numerator backwards. They say pq prime minus qp prime over q squared. That's wrong, but it's wrong by a negative sign. So you've reversed the order. So it's wrong, but it'll be wrong by a negative sign, and for that I take off half a point, but it's half a point every time you do it, which can get costly, so don't do that. All right. So here in our problem, our p is the x, our q is the x plus 2. And so therefore the derivative f prime is denominator times the derivative of the numerator. So the derivative of x is just 1. Minus the numerator times the derivative of the denominator. Well, the derivative of x is 1. The derivative is 2. It's just a constant. Its derivative is 0 over x plus 2 squared. Are you okay with using the quotient rule? Now, on the first midterm, you can just leave it like that. You don't have to simplify on the first midterm. On the second midterm, though, you see you're going to be using this. So, first half of the course, first midterm, is all about how to find the derivative. Second half of the course is what's it good for? What are the uses of the second derivative? First derivative. So you need to use this in the second half of the course. And so to use it, you need to simplify. Is it okay 1 times anything? So x plus 2 times 1. Subtract. This is just 1 times x over x plus 2 squared. And so you notice x subtracts x, and it nicely comes down to 2 over x plus 2 squared. So as I say, you've got to do that on midterm number 2. If you leave it this way for midterm 1, that's fine. That's fine. On the first midterm, sometimes people go ahead and they start simplifying it. And if they make a mistake and they're simplifying, I'm not going to take off points on the first midterm, because that's all I ask you to do. But if you go ahead and simplify anyway, and you make a mistake, I'm going to point it out to you, because you need to practice your algebra. So I'll circle your mistake, give you a frowny face, whatever. But no points off on the first midterm. You can leave it unsimplified on the first midterm. Number 21. Here we have f of x is equal to e to the x over x minus 2. Okay. Remember, e is that funny function, which is its own derivative. Let me just remind you, if I want the derivative of e to the x, it is just itself. That's the funny property of the number e, 2.71828. It's the only number that does that. But while I'm here, let me just remind you, that's a horse of a different color. There's no x there. E is just a constant, 2.7. You get the distinction? Here, you have a function of x. Here, it's just a constant. You know, if I ask you for the derivative of pi, 3.14159, that's just constant. Its derivative is 0. Would I throw something like this at you on the first midterm? Sure. See if you're awake. The derivative of a constant, 117.5. It's a constant. Its derivative is 0. But e to the x is a function of x. It is its own derivative. So let's do the quotient rule here. Quotient rule says denominator times the derivative of the numerator, but remember, e to the x is this one function that is its own derivative, minus numerator times the derivative of the denominator. The denominator, the derivative of x is 1. The derivative of negative 2, it's just a constant, all over x minus 2 squared. And indeed, if you left out the 0, that's perfectly fine. I'm just putting it there for emphasis. You can leave it out. So if you gave me that for the first midterm, I'd be happy. But now for the second midterm, you got to simplify, because you're working with it. Do you see how it simplifies? You have x e to the x minus 2e to the x minus e to the x. Negative 2e to the x minus e to the x. Isn't that negative 3? X e to the x minus 3 e to the x, x minus 2 squared. So as I say, on midterm 2, you need to simplify it because you're working with it. Here with midterm number 1, just leave it like that. It's fine by me. Yeah, number 29. Y equals u squared minus 1 over u cubed plus 3. Yeah. This is a function of u. And Stewart loves to screw around with naming the independent variable. Here, instead of x, is using u. All right. So we want df with respect to u. Now you see, here is where this d notation has an advantage over our prime notation. The prime notation is easier to write. F prime means derivative. But here, df du, the advantage of the d notation is that at every stage it reminds you as to what the independent variable is. Here he decided to name it u. I mean, usually we use x or t. X stands for quantity, t stands for time. All right, he's using u. Let's deal with it. Denominator times the derivative of the numerator, u squared goes to 2u, and the derivative of negative 1 is 0, minus numerator times the derivative of the denominator. Well, u cubed goes to 3u squared, and the derivative of 3 is just 0, over u cubed plus 3 quantity squared. Is that okay with everyone? And as I say, on midterm 1, leave it that way. You don't have to simplify. But come midterm 2, you're working with it. So yeah, you have to simplify it. So you have to be able, are you okay with the algebra? You know, the nice thing about big classes is somehow you feel less self-conscious about asking questions. I've had classes of 4, 5, 6 students, and they just feel too self-conscious to ask questions. If I'm doing some algebra thing here and you're not following me, please ask. You know, I realize that with COVID, a lot of you have got a hole in your algebra. So if I'm doing something that you don't see, please ask. So here I'm going to distribute the 2u. I like to save orange for steps. I'm distributing 2u over these parentheses. So that gives me 2u to the 4th, right? U cubed times 2u, add powers. 2 times 3 is 6u, minus. And what am I getting here? 3u to the 4th minus 3u squared. Is that okay? I distribute the 3u over 3u squared over the parentheses, and I have u cubed plus 3 squared. And now, maybe you would have done this step in your head, and it's perfectly fine if you do it. I didn't because I want to make a point. Remember, this negative sign distributes with both of these terms, making this one plus, because it's minus minus. 2u to the 4th plus 6u minus 9u to the 6th minus 3u squared all over u cubed plus 3. You know, I made a mistake. I don't know what I think I'm doing. I take this negative sign, and I'm distributing it over the parentheses. Where on earth did I get 9u to the 6th? That's stupid. It's 3u to the 4th. I'm sorry. 3u to the 4th. And so 2u to the 4th minus 3u to the 4th is negative u to the 4th plus 6u plus 3u squared over u cubed plus 3 squared. And that's as far as you can go. Is that okay? Now, I don't know if you've been watching me, but sometimes when I went to write a u, I started writing an x, because I'm so used to thinking of x or t as the independent variable. What I'd like to do, I mean, this 29 is a good problem. Let me redo the thing just using the letter x instead of u. It's exactly the same thing, but you guys are struggling hard enough to learn these rules without throwing different letters at you. Let me redo 29 in terms of x. .2, I'm going to redo problem 29. Only instead of the letter u, I use the letter x. So the function we're given in 29 is x cubed minus 1 over x squared plus 3. And so, we want the product, sorry, quotient. Quotient. So f prime, alias df dx. So the prime notation, that's the English notation after Isaac Newton. It's shorter. It's just prime. But this D notation after Leibniz in Germany, it's longer, but it has the advantage of reminding you what the independent variable is. Yeah?
X squared minus 1?
Did I miscopy? So x cubed minus 1 over x squared. So this is supposed to be a 2.
No,
That's x squared plus 3.
I thought the top one had to be, maybe I miswrote it, I don't know.
Yeah, that's x cubed.
I think it's talking about the one you just did before this one. Like the one with the U.
Ah, shoot. I miscopied the U one. I'm sorry, I miscopied this problem. So I believe this work is correct, but it's the wrong problem. Because number 29 has the cube there and the square there. Sorry about that. I miscopied it. So I'm glad I'm doing it again. Yeah, thank you. So the cube was in the numerator, the square is in the denominator. Okay, now it's right. Okay, and so the quotient rule says denominator times the derivative of the numerator, that's a 3x squared, right? X cubed, the 3, the old power is the new coefficient, new power is 1 less. 3 subtract 1 is 2. Minus numerator times the derivative of the denominator. X squared, the derivative is 2x, And plus 3 is just a constant, its derivative is 0. Over the denominator squared. And as I say, midterm 1, leave it that way. But you have to be able to simplify, and you see what I'm going to do? I'm going to distribute that factor over these terms, distribute this factor over these terms. So there's a 3x to the 4th, add powers, plus 9x squared, minus, here distribute, 2x to the 4th, minus 2x. And indeed, you probably would have done this in a single step, but I just want to emphasize, I did it in 2 steps because I want to emphasize that that negative goes with both terms. So this is 3x to the 4th plus 9x squared minus 2x to the 4th minus a negative 2x over x squared plus 3 squared. And as I say, a common mistake when you're simplifying, people often make that negative because they forget you're subtracting a negative, which is a positive. And now you have a little cancellation. 3x to the 4th minus 2x to the 4th gives you 1x to the 4th. And 9x squared plus 2x. Am I okay this time? So on the second midterm, you have to be able to simplify. Am I okay this time? And so what I wanted to say about this, you know, I'm not going to, x is quantity, t is time. So x and t are the only independent variables you really use. But say if you had u's, let me copy it right this time. U cubed minus 1 over u squared plus 3. And then you start using your quotient rule. And let's say that you were to slip to x. Denominator times the derivative of the numerator minus the numerator times the derivative of the denominator over the denominator squared. Say that if you slipped and you started writing x's instead of u's. Fine, no problem. What's important is the rule. What is important is being able to do the quotient rule. Okay. 35. Let's see. A large corporation already has quartered 20% of the disposable alcohol market and now wishes to undertake a very extensive advertising campaign to increase its share of this market. It is estimated that the advertising cost, C of X, in billions of dollars, of obtaining an X% share of this market is given by C of X. What is the marginal cost? Okay. So the key word in this problem is marginal. Oh, yeah. Yeah, this is a good, this is a good problem. And in fact, before I do this problem, Let me do a preliminary example, then we'll do this. What if I gave you f of x is equal to, let's make it 1 over x squared plus x plus 1. And we're going to use the quotient rule on this. Notice that my numerator is just the number 1. The numerator alone is a constant. So when I go to take the derivative of the numerator, it's 0. So if you think of this as p over q, the derivative of p over q is denominator times derivative of numerator minus numerator times derivative of denominator over denominator squared. But if my p is just the number 1, when I do p prime here, is that okay? P prime turns out to be 0. Okay, so let's do this. I want the derivative of 1 over x squared plus x plus 1. So my rule says denominator times the derivative of the numerator. The numerator is just 1. Its derivative is 0. Minus numerator, which is just 1, times the derivative of the denominator, 2x plus 1, over the denominator squared. The mistake is people see 1 and somehow they feel as though p prime shouldn't be 0, so they end up putting a 1 there instead of a 0. No, the numerator is a constant, so its derivative is 0. Let me do another example, and then we'll do the marginal cost. Let's say that I have 3 over x plus e to the x. You see what I'm trying to emphasize. The numerator is just a constant, 3. Its derivative is 0. So when you do your rule, denominator times the derivative of the numerator is just a 3. Its derivative is 0. Minus, now numerator, which is 3, times the derivative of the denominator. The derivative of x is 1. The derivative of e to the x is that funny function, e to the x over x plus e to the x squared. So if you simplify this, 0 times anything is 0. And you have negative 3, 1 plus e to the x over x plus e to the x squared. Are we okay? So if your numerator is a constant, its derivative is 0. Okay, 35. We don't really need the discussion. They simply have given us a cost function. 1 over 10 minus 0.1x. And what they ask for is marginal cost. Now, how did they explain marginal cost to you back in economics? They said, okay, If your cost for X item, C of X, is given by that, marginal cost means pay for one more item. What does the cost, what is the increase in cost in purchasing one more item? Well, this is why you're taking calculus, because it's so much easier simply to take the derivative. Marginal cost simply means the derivative. And it amounts to the same thing. How much would one more item cost you? Well, let's use our quotient rule here. Denominator times the derivative of the numerator. Your numerator here is just 1. Minus numerator times the derivative of the denominator. Well, the derivative of the denominator, derivative of 10 is 0. And so you've got a coefficient of negative 0.1. And the derivative of x is just 1 over the denominator squared. Is that okay? You want the derivative of the denominator. The derivative of 10 is 0. Negative 0.01 is a coefficient. The derivative of x is just 1. So if you simplify all of that, 0 times anything is 0. And here you have minus a negative 0.1 over 10 minus 0.1x squared. Find the marginal cost, and there you are. And they're not asking you to do anything else. So the problem is finished. I'm just thinking about this a little bit. Yeah. X represents, X is the percent of the market you sell to. So your impression would be, you would like to capture as much of the market as you can. But there's a limit to that. Trying to capture too much of the market would drive your costs sometimes too high. Imagine, if you tried to capture 100% of the market, look at what happens to your cost. If X is 100%, 0.1 is 10, 10 minus 10 is 0, you have a 0 in the denominator, which means this becomes huge. It costs you a huge amount of money to try and capture 100% of the market. And so marginal cost is asking you, okay, how much of the market do you want to capture? That's when your marginal cost is 0. Okay, so I really am now talking more economics than I'm talking calculus. The calculus problem is finished. But you guys are econ majors, business majors, and you're asking yourselves, why do we give a damn about this stuff? So I'm trying to say something economically. There comes a point in time in which trying to capture more of the market simply becomes too expensive. Clearly, if you try to capture 100%, you're dividing by 0, which is an infinite amount of money. So even 90%, I would try 90. So the question is, when does your marginal cost turn to 0? Yeah. You want to capture as much of the market as is profitable to you. If it costs too much, you don't want your profits to go, you don't want your profits to tank. And so you want your marginal cost to equal 0. This is what we're going to get into in the second midterm. Things are maximized where the derivative is 0. So profit is going to be maximized where marginal profit is equal to 0. That's where we're heading with all of this stuff. Okay? That's why you're being taught calculus. Okay. Okay. So that does 4.3. Sorry, 4.2. Now we're looking at 4.3. And 4.3, you know, you've seen the product rule is useful. You've seen the quotient rule is useful. The most useful rule of them all, though, is now what's called the chain rule. And so my idea now is to try and get across how to use it. Why it works is not that important to us. Yeah, it comes from the limit definition. And just like product rule, next time I will wave my hands at a proof of the chain rule. You don't need to know the proof. The only reason I'm going to mention it is it might help ram home how to use the thing. Okay. So here's how you use it. We have talked about the power rule. The power rule is when you're trying to take the derivative of a power like x to the n. And what we have learned is the power rule says the old power is a new coefficient, the new power is one less. The chain rule starts the same way. The chain rule it's dealing with the same situation, only instead of just a simple x underneath the n. Let's say you've got something more complicated. I'm going to call it box. Do you remember back in, what, 8th grade, and they started teaching you algebra? Before they introduced the letter X, did they have a box? So maybe in baby algebra, when they started this on you, maybe they said something like, okay, 3 times what is 15? 3 times what is 15? And did they say, you know, if we write an equation, turn that sentence into an equation? Did they say, well, let's call what the box? 3 times box is 15. And then did they say, well, we let the box be represented by a variable x. So 3x equals 15. There's an algebraic equation. And so you divide both sides by 3, you get x equals 5. Okay, my only point was, do you remember way back in baby algebra? They might have used a box to stand for something. Let me use the box here to stand for X, or maybe something more complicated. The chain rule says you begin by doing the same thing. Step 1. This is step 1. If you got something to the nth power, the chain rule says, okay, deal with the outer function, box to the n, just like you normally would by the power rule, n box to the n minus 1. Step 2, though, now, multiply by the derivative of what's inside the box. That's how you use the chain rule. I just want to do today a few examples, and Wednesday then I will try to wave my hands at an explanation as to why it should be true. You don't need to know the why, you only need to know the how. So for example, let's say I ask you for x squared plus x plus 1 to the 17th power. Well, it sure would be a pain to try and expand that to 17th power, wouldn't it? What a pain. So what you do is the chain rule. And the chain rule says, look, step 1, ignore the inside of the parentheses. Just call it box. Just call it box. So if you've got box to the 17th, what do you say? 17 box to the 16th. That's your first step, where you recopy the inside. Step 2, you multiply by the derivative of the inside, which now is 2x plus 1. The derivative of x squared is 2x. The derivative of x is 1. Derivative of 1 is 0. That's an example of the chain rule. Let me do another example. Let's make it x cubed plus e to the x cubed. Okay. Chain rule says, let's first look at parentheses. What is outside of the parentheses? That's your box. This problem is essentially box cubed. Problem is essentially box cubed. And if I said box cubed, what's the derivative? You'd say 3 box squared. So ignore what's in the parentheses for a minute. Or if you wish, call what's in the parentheses box. And now box cubed becomes 3 box squared, where you recopy, don't change the inside of the box. Step 2, you multiply now. Now look inside the box. Now take the derivative of the inside. X cubed is 3x squared. And the derivative of e to the x, remember, it's one of those funny functions. It is its own derivative. Let me do another example and then show you what not to do. Let's say you've got x cubed minus 17x raised to the 13th power. Here's what you do. Call what's inside the parentheses box. Call that box. You had box to the 13th. The derivative is 13, box to the 12th. Old power, new coefficient, new power 1 less, where you keep the inside as is. Now step 2, multiply by the derivative of the inside. Now look inside the box. X cubed goes to 3x squared, 17x goes to 17. You're done. Now I'm going to grab my red pen. Don't do this. I'm not sure why. A lot of people put a plus there instead of a minus. Everything else will be okay. But then they add them instead of multiplying them. And, you know, every mistake in math is the right rule in the wrong place. And for years I tried to understand why are people putting a plus there. And last year someone said, oh, what they're doing is that they're thinking about the product rule. You know, product rule, you get the mixed sum, p prime q plus pq prime. That's what they're doing. No. Chain rule, it's multiply. And then the other mistake is this. They'll do the box prime okay. They'll do the box prime okay. But then they stick the derivative on the inside. And I can sort of understand why. Because if this is nested, shouldn't your answer be nested? If this is inside of that, shouldn't that be inside of that? Well, no. I can understand where that comes from. But no, that's not what you do. Again, you do the derivative of the outer. Call it box. Box 13th. Do box 13th. Then multiply by the derivative of the inside of the box. So on Wednesday, I'll try and just wave my hands at why that should be true. But what's important is that you be able to do it. See you Wednesday.